Okay, this is Mr. Flamino again, picking up where we left off with section 2.4 with our definitions of functions. In this section, we're going to talk about function domains, the graphs of functions, and some other characteristics in there as well. So for function domains, it's going to be, remember that set of inputs. They can be described explicitly or implied by the expression that defines by the function. Now, described explicitly, this piece right here, would have some piece after a function that says only use these values. For example, if we had a function f of x equals 3x plus 1, and we followed that with a comma or a semicolon and said x is an element of the closed interval from -4 to 7. In that particular case, what we would be saying is while this is a linear function, which is normally defined for all real numbers, in this particular case, we only want to use this linear function for x's that exist between -4 and +7. So that's what described explicitly means, is that after the function itself, there is a statement of an interval, of an inequality, or maybe even a verbal statement that says which inputs should be used for that function in that particular case. And that's normally used when the domain that we want is more restrictive than what would naturally occur had we just left the function alone by itself. For example, like we're saying here in this particular case, the linear function 3x plus 1 would normally be defined for all real numbers, but we want to restrict it down and only take part of that. So that's what described explicitly means in that particular case. Most functions, however, that we deal with are going to be of the nature when we want to look at what is implied by the expression that defines the function. The two major things you need to look for domains that we need to avoid, I'll even put this down here, we need to avoid these two things. First one being negative values under what we might call even radicals. In algebra 2, you would say that we want to avoid negatives under square roots. But now that we've studied roots of other indices, things like 4th roots, 6th roots, 8th roots would be even radicals, because those would put us into the imaginary numbers. And we just don't want to deal with that stuff for the most part. And the other thing that we want to avoid are zeros in denominators. And it's not that we want to avoid using a 0 in the denominator. We want to avoid using a value for x that results in the denominator being 0. Excuse me, the denominator being 0. And we'll look at both of these cases in the two problems I have on the board that we will demonstrate now. So if I take f of x equals 1 divided by x squared minus 4, I have to think to myself, well, I don't have any radicals, but I do have a denominator. And if indeed the x squared minus 4 was equal to 0, that would be bad for us because we'd have an undefined value. So that means if x squared minus 4, we don't want that to be 0. That means x squared, we don't want that to be 4 by adding 4 to both sides. Take the square root of both sides, x equals plus or minus 2. And remember, all of this would be bad and bad. And so what that tells me is that the domain of the function f for this particular problem is all real numbers except the numbers plus 2 and negative 2. And I could write that a variety of different ways. Using interval notation, or one way of writing it would be to say that x is an element of the set of all real numbers. That's the symbol for all real numbers with that double vertical slash on the r. And from that, we're going to write a minus sign. And we're going to use curly brackets. And I'll write plus or minus 2 and close that with a curly bracket. And whenever you see that notation, that says that we have this set of all real numbers. Remember, a set is a collection of numbers. So we have this collection of numbers, a pile of numbers, if you want, of all the real numbers. And from that set, we want to remove, and subtraction in this particular case can be remove the numbers positive 2, remove the number negative 2 from the pile. And all the numbers that are remaining are the numbers that can be used as inputs into the function. Now that has very big implications towards what the graph of our function looks like. And we'll get into that later on in the year. So anyways, that's a domain example for that. On the other hand, for the second function we're looking at, f of x equals the square root of x, well, we have to make sure that the value underneath this square root, this x, cannot be a negative number. So I would follow a similar setup, and I'd say, well, if x is a negative number, that would be bad. This particular case, there is no other work to be done with it. It's just like that. And so the way I would write this is I would say, well, that means x can be. That means x being greater than or equal to 0 would actually be good. So writing this as an interval form, I would write x is an element of the half-closed interval from 0 to infinity. So that's the domain of this function here. X is an element of the half-open interval, starting with 0, writing to infinity. When we solve for a domain, we generally start with looking at what values would be bad for us. But when we actually go ahead and write the domain, we're going to actually write what would be good for us. When I took my real numbers and removed the two bad numbers, the pile that was left was everything that was good. And when I wrote this, that's all the numbers that would be good for me. I don't want to know what's not in the domain. I want to know what actually is in the domain. I think I'll do one more example. I think I'll do one more example with you, and I'll leave the rest of the examples to be done in class between you and your teacher. Just another example here. Let f of x equal the square root of x minus 2. Find the domain of f. I have to say to myself, well, what is under the radical has to remain 0 or positive. And so I need to make sure that x minus 2 either equals 0 or is positive. And I could either do this from the good standpoint or the bad standpoint. I could either write, say, well, if x minus 2 is negative, that would be bad. But that's equivalent to saying that x minus 2 being greater than or equal to 0 would be good. And so how am I going to write what is good? I'm going to take this x minus 2 greater than or equal to 0. I'm going to add 2 to both sides so that x is greater than or equal to 2. This would continue to be a good thing for us. And now I just convert it over to interval notation. X is an element of the half-closed interval, beginning with the number 2, going to infinity. And those would be all of the good numbers. So, there are, but those are the two basic things we look for. Remember that we want to make sure that what is under the radical would always be positive. That would be good for us. And also that what is in the denominator of a function that has a variable in the denominator cannot equal 0. Now, we can use 0 as an input. For example, in this case, if I use a 0 in place of the x, I get 0 squared minus 4. And my denominator is negative 4. So that's fine. So it's not that using 0 is bad. It's getting a result of 0 that would be bad. So just keep that in mind. So just a little work on function domains. We're going to do a lot of work with domains and ranges throughout pre-calculus. This is our introduction, getting a little bit used to it. The second thing we want to talk about in this video are the graphs, and really making the connection between the algebraic representation, that's our equation or our rule, and the graphic representation. And graphs are really good ways to indicate how f of x changes as x changes throughout the domain. And let's put a couple more words in here. And when I say the change in f of x, another way of saying this is saying the change in the output as the input varies throughout the function. If I simplify it down a little bit, put it in a little bit of words to make them a little more understandable, we might say that we want to know how our outputs change as our inputs change. So as our x's get bigger, what happens to our y's? As our x gets smaller, what happens to our y's? And then we start to say, well, what happens if x goes to infinity or negative infinity, or x gets really close to 0? And when we start talking about a little bit in pre-calculus, but it's really heavily emphasized in calculus. And so we kind of get a jump on it while we're working on it throughout this year to prepare us for it. Now, just a little bit of a definition here. The graph of a function f is the graph of the equation y equals f of x for x in the domain of f. And all this really says is that the y coordinates on the graph are the same thing as the outputs of the function f. Remember that when you see the f by itself, that is simply the function name. But when you see f of x, it's referring to function outputs. So whenever we see an f of x in our heads, we have to think outputs. So it's just saying that the y coordinates on our graph are the same as the outputs of the function. It's just a fancy way of saying it. But math is filled with fancy language, and sometimes we just need to get used to it. And what that says is for each point A, B on the graph, the y coordinate of the point B is the function value of A. Huh? Well, you pause the video for a second, write that down, unpause it, and come back, and I'm going to draw a picture to demonstrate. If I have the graph of some function, let's say I have the graph of this function, and on this function, I have the point P, whose coordinates are A and B. Well, from here, that means that this x coordinate is A, and the y coordinate of that point is B. What we saw on the last slide is what we're really doing with a function is we're taking this value of A, putting it into the function. That means if I have some function f, I am evaluating f of A, putting A into f, and getting out some output, and that output is B. So the statement above where it says B is the function value f of A is my statement right here. We're just trying to make some connections about notation, algebraic notation, with the graphic representation of it, so we can understand and progress through pre-calculus and calculus, so on and so forth. Remember, for the definition of a function, each input paired with exactly one output. And that leads us into some interesting statements that really help us with our graphs. That means for each input A, for each input in the function A, there is only one possible value for f of A. If I evaluated f of A and I got out two values, some b sub 1 and some other b sub 2, that would be bad. We wouldn't have a function. The definition states that each input, my input is A, is paired with exactly one output. Well, there I'm paired with two outputs, b sub 1 and b sub 2. And in the last video, you'll recall that we talked about ambiguity. Here, I'm putting in A. What am I getting out? I don't know. Might be b sub 1, might be b sub 2. When you have that case, not a function. And this leads into another thing. That means on the graph, for each x coordinate A, we can only pair it with a single y coordinate B, also known as f of A. And this whole idea, this train of thought from step 1 to step 2 to step 3 on the slide, leads us into our old friend, the vertical line test. And the vertical line test says the graph of a set of points in a coordinate plane is the graph of a function if every vertical line intersects the graph at most at one point. If we intersect the graph at more than 1 point, let's say 2 points or 3 points, we have failed the vertical line test, and we have failed to be a function, because that would fail all of this right here. Let me give you an example. If I have my coordinate plane, and I have a graph, and let's say my graph looks like this. And I draw some vertical line through there. Now, I have 3 points of intersection with this vertical line. Here, oops, not there, here, and here. And what I do know is that those 3 points all have the same x-coordinate. And let's call that x-coordinate A, because that's what we've been doing. We'll just kind of keep it the same for now. But all 3 of those points have different y-coordinates, and they might be b sub 1, b sub 2, and b sub 3. And that leads into a violation of what we had on the last slide. I would have, in this particular case now, f of a equals, well, I don't know. It might be b sub 1. It might be b sub 2. And it might be b sub 3. Not a function. Failing the vertical line test basically says that you are failing the definition of what a function is. And therefore, it's not a function. Just as a point of emphasis, the vertical line test is not the definition of a function. It tests, let me do that in a different color there. It tests to see if a relationship fulfills the definition or fails that definition of each input being paired, I better spell that correctly, huh? Paired with exactly one output. It tests it. And it's fast. It's a good, real good, fast test. I think I'm going to leave this example to be done in class with you and your teacher. And I'm going to move on to increasing, decreasing, and constant functions. That'll be our last item in this video. I will do an example at the end here. Increasing functions say that, we'll give a definition here. A function is increasing on some interval. And let's define the interval from x sub 1 to some x sub 2. If f of x sub a is smaller than f of x sub b for every, that's what that symbol means, for every x sub a being smaller than x sub b. I know, you're saying, huh? Well, what it's basically saying is that whenever you have the smaller input, always gives the smaller output. And the bigger input gives the bigger output. So we could say that as the inputs increase, the outputs increase. And I know the word increase is in there twice, but which increase is the important increase to look at? It's the increase for the outputs. It's always about what the outputs do. What does this look like graphically? Now, if I take my coordinate plane, and if I have some x sub a and x sub b, where x sub b is larger than x sub a, and I have then some situation where my f of x sub a is smaller than my f of x sub b. That creates 2 points right here. And essentially, my graph is going to go up. But it does not have to go up linearly. It just has to go up the whole time. If I erase that line and I had my graph look like this, and it's true. As my x's get bigger, as I were to choose successive x's, larger and larger between a and b, my y's are getting larger and larger. So the line, the increasingness, does not necessarily mean linear. It just means as we work throughout that particular interval, it does increase. And it could increase this way, or the way I showed before. We could have all sorts of variations there. but that's what an increasing function is. And knowing where functions are increasing, decreasing, and constant, very important ideas in pre-calculus and especially calculus. The next one is a decreasing function, and it says a function is decreasing on some interval if f of x sub a is larger than f of x sub b for every, I'm not going to have enough room to write it there, let me erase that, for every x sub a less than x sub b. So that's a little bit different than last time. It looks a little bit different. But what we're going to get at here is sort of an opposite relationship. X sub a is the smaller of the inputs because it's smaller than x sub b. But the result, the output for the smaller input is larger. The smaller input has the larger output. X sub a is the smaller input, but f of x sub a is the larger output. And x sub b is the larger input, but has the smaller output. If I want to put a similar phrasing onto it as I did before, I would say as the inputs increase, because I'm still speaking of them, x sub a is smaller than x sub b, the outputs decrease. And so once again, we're seeing it's what the output does in terms of that to make this considered a decreasing function. So we'll do the same thing here. We'll determine what this looks like graphically as well. If I draw my coordinate plane and I choose an x sub a that is smaller than an x sub b. Now I've got to be a little more careful now because my x sub b had the smaller of the outputs. So that's going to be f of x sub b in the lower position and my f of x sub a in the upper position. And that will create a point here and a point here. And I need to connect them. And I may very well connect them with a straight line, and it's decreasing. As my inputs increase, as I go from x sub a to x sub b, my inputs get bigger, but my outputs decrease. So thusly, we call it a decreasing function. And like I said before, it does not have to be linear. The simplest one is the linear one, but it could be a curve like this, or it could be some other curve, maybe like that, decreasing function. So that's what we have for decreasing functions. The last of these three is a constant function. And you may be able to figure out what that means now. But it says a function is constant on some interval if f of x sub a is equal to f of x sub b for every x sub a and x sub b. This one's a little bit different, and x sub b in the interval. So it's like, the word constant, a constant value throughout. And it's just saying, it says no matter what input we have, whether we have x sub a or we have x sub b, we choose any value in there, and the outputs that we get are going to be equal. That's all it's saying right there. If I want to put this into words, it just basically says no matter the input, the output is the same. And that's what the math version of the word constant is, means the same. Graphically, I know I'm picking up the pace a little bit here, but this is kind of our third time through, and it's kind of all the same stuff. And it says if I have some x sub a and some x sub b, right here, f of x sub a and f of x sub b are going to be the same. Gives me a point, gives me a point. Maybe I should choose a different color here, maybe something that pops. How about a red and a red? And I have to connect them, and they have to be the same. Now, that one has to be a horizontal line. And that's saying no matter what value of x I choose between x sub a and x sub b, I'm always going to get that y coordinate. And that gives me the picture that I have. Note in all three cases, I said on some interval. Some interval, some interval, some interval. Most functions are not either all increasing or all decreasing. They're some of a little bit of both. So I have an example here where we're just going to skip straight to number 2. I'm not going to cross that out there. We're just going to skip straight to number 2. You can do number 1 in class with your teacher. But find the intervals where f is increasing, decreasing, or constant. Just to make life easy, I'm going to put some dots at the end of this graph so it doesn't continue forever. And I'm going to look at this and say that I have four pieces to look at. I have this piece right here as 1, this piece as 2, this piece as 3, and this piece as 4. And for me, I'm looking at the yellow piece and the green piece, and I'm saying that those pieces are increasing. So I'm going to write an NIC for increasing. And I'm just going to write where it's increasing in the form of an interval. My x is an element of. It starts at -10, and it's increasing until x is equal to -3. That's where my yellow segment ends. And then I've got another one, so I'm going to union it. Starting at x equals 0, that's where the x coordinate of my green segment starts. And it goes till 4, and that's where the x coordinate of my green segment ends. So that's where those functions are increasing. For the decreasing functions, it only looks like the red portion there. And so I'd write x is an element of, and that red portion that I highlighted starts with an x coordinate of -3 and ends with an x coordinate of 0. I'll close that up. And that's the only segment that's decreasing. So that just simply ends there. There's no second piece to union with. And then I would have a constant piece. And that seems to be the horizontal piece covered in blue over there. So x is an element of. And my blue segment starts at an x coordinate of 4. And because it's a dot on the end and it's a closed dot, it's a 10 with a closed bracket there to say included. And we could have variations. Had these been open circles or had arrows on the end, we could have a variety of different things shooting off to infinity. But that's just a little introduction to domains, graphs, increasing, decreasing, and constant functions. I hope you find it helpful. When you go back to class, there will be more examples to help support this, but it should get you a good start. Thank you.